Hi folks! Do you have an exam coming up in something like applied cryptography, or introduction to discrete mathematics, or some kind of algebra, or virtually anything else that involves modular arithmetic? Do you not feel completely convinced in your ability to evaluate expressions modulo n? Today we are going to take a look at some tips and tricks that you can use to make your life a little bit easier. Alright, so let's start with a brief recap of what this modular business is all about. We're interested in relations like this, and this is pronounced A is congruent to B modulo n. And what this means is that if we divide A by n, we're going to get B as the remainder. Now, this second line may look a little bit confusing. This is how we used to write division with remainder when I was in primary school, or was it kindergarten? But if you're more mathematically inclined, you may prefer notation like this. We divide A by n, we get quotient S and remainder B. And here it's important that the remainder is between 0 and n minus 1. For a practical example, we can try to find the value of 20 modulo 7. So we need to divide 20 by 7 as integers. We're doing integer division. If we're to divide them like real numbers, we would get a fraction, 2 point something, 857. And this is not what we want. Instead, we can write 20 as 2 times 7, because 7 goes 2 times into 20, and we get a remainder of 6. And this means that 20 is congruent to 6 modulo 7. And we can also write this the other way around, because this congruency operator is an equivalence relation. So it behaves pretty much like equality. If A is equal to B, then B is also equal to A. Now, an important observation is that adding or removing multiples of 7, as in this example, is not going to change the result. We know that 20 is congruent to 6 modulo 7 because we can write it as 2 times 7 plus 6 as a remainder. If we add 7 to 20, then this is not going to change the remainder. We are just adding 7 one more time. And similarly, if we subtract 7, we are going to get 1 times 7 instead of 2 or 3 times 7, but the remainder stays the same. Now, it's quite obvious that 6 is congruent to itself, modulo 7, and modulo anything, really, but more formally, we could write it as quotient 0 and remainder 6. And by continuing to subtract multiples of 7, we can also express negative numbers. Minus 1 and minus 8 are still congruent to 6, modulo 7. This means that if we want to compute something modulo something, for example, 27 modulo 7, one way to do it is to just keep adding or subtracting 7 until we get a number between 0 and 6. And because this congruency is an equivalence relation, which again acts like equality, we can write expressions like 20 is congruent to minus 8 modulo 7, because they give us the same remainder when we divide. We can also chain expressions together like this, just like with equalities. But if we are asked, what is 27 modulo 7? So if we treat modulation as an operator, as a function that takes two numbers and gives us one output, then there is only one answer. And this is why we have the restriction that we need a number between 0 and n minus 1. If we are computing 27 modulo 7, then the canonical answer is going to be 6. Typically, when you encounter modular arithmetic, you don't just want to compute A modulo B. Typically, you have an expression, not unlike this one, which you need to evaluate. And here you can have addition, multiplication, exponentiation, subtraction, and possibly some other classic arithmetic operations. Now, one way to do this is to just compute everything, forgetting about the modulo 10, and then modulate. So we simplify the expression on the left-hand side as normal. 8 times 12 is 96, 2 to the power 3 is 8. We compute the result, getting 98. and then we compute the remainder of this modulo 10, which gives us the answer 8. But a very important observation is that we can apply arithmetic operations and modulation in any order that we choose, and this can frequently lead to simpler computations. For example, here, in the same exact expression, we can see that 12 is actually larger than 10. And obviously 12 modulo 10 gives us 2. So now if we replace this 12 by 2, we're going to get a slightly simpler expression. 8 times 2 is easier to compute than 8 times 12, right? But if we simplify the expression until we get the final result, we are still going to get 8, which is the correct answer. And in fact, we can push this even further. So if we consider the same expression again, we can try to look for numbers which look suspiciously large, meaning numbers which are larger than 10 or very close to 10. For example, 8. 8 modulo 10 is still 8, obviously, so we cannot reduce it by modulation, but because 2 plus 8 is equal to 10, we can actually rewrite 8 as minus 2. 12, as we have seen before, is just 2 modulo 10. And then we have 9. 9 plus 1 is 10, so in fact this is minus 1. 2 to the power 3 is 8, and we have in fact already seen that this is nothing else than minus 2. And now I think you will agree that the expression that we get in this way is significantly simpler to evaluate, because we have numbers of much smaller absolute value. And if we do the computations, we end up with minus 2, which modulo 10 is of course the correct answer, 8. So basically, if you're a bit careful and try to think strategically about when to apply arithmetic operations and when to modulate, you can end up with significantly simpler calculations. Sometimes, and actually quite frequently, you are given an exponent that you want to compute. For example, 3 to the power 20 modulo 24. And this occurs, for example, in some cryptographic ciphers like RSA. In any case, this means that you just have to multiply 3 by itself 20 times. And if you're smart, you can of course modulate in between steps. But when you have an expression like this, it's usually worth it to try and see if there are any patterns in the exponentiation behavior. So what happens if we multiply 3 by itself several times? We see that 3 to the power 2 is 9, which is true anywhere, but 3 to the power 3 is 27. And 27 modulo 24 is 3. So in fact, if we raise 3 to the third power, we go back, right back to 3. So let's see how we can use this to simplify our life here a little bit. We want to compute 3 to the power 20, which we can actually write like this. If you look at the sum of the exponents, we have 6 3's and 1 2, and that obviously sums to 20. So this is the expression that we want to compute. But because 3 to the power 3 is the same as 3, each of these exponents, each of the first 6 terms of 3 to the power 3 can be replaced with just 3. So now we end up with 3 to the power 6 times 3 to the power 2. And again, we can decompose it as 3 to the power 3 times 3 to the power 3 times 3 to the power 2. The 3 to the power 3's we can substitute with just 3. And then we get 3 to the power 4, which is 3 to the power 3 times 3. And 3 to the power 3 is 3, so we end up with just 9. And I'm sure you will agree, this was much easier than computing 3 to the power 20 and then modulating. So far, we have seen how to add, multiply, subtract, and exponentiate modulo n. But sometimes one wants to divide. And occasionally this can be quite easy, and we can follow the approach where we do the arithmetic first, so we divide 20 by 5 as usual, and then if really necessary we modulate. So in this case we would just get 4. But sometimes this is trickier, because 20 divided by 7 is not an integer that we can modulate by 27. And to figure out how we can approach divisions like this, we need to take a step back and think about what division actually means. Now let's just assume 20 and 5 are real numbers. Dividing 20 by 5 is essentially the same as multiplying 20 by 1/5. And 5 and 1/5 are two real numbers which are connected by a very special property, namely their product is equal to 1. We call such numbers inverses of one another. And in general, for any element x, anywhere, modulo 27 or over the real numbers, we can define its inverse, which is typically written as x to the power minus 1. An element x and its inverse are connected by the property that their product is equal to 1. And if we wanted to be formal, we could write that over the real numbers, the inverse of 5 is 1/5. Now back to modulo 27. To divide 20 by 7, what we actually want to do is we want to multiply 20 by the inverse of 7. And this inverse is one of the integers between 0 and 26, which has the special property that when multiplied with 7, we're going to get 1. One simple way to find it when the numbers are sufficiently small is to just brute force it. Let's just take all numbers 0, 1, 2, 3, etc., multiply by 7, modulate by 27, and see if we get 1. Well, 0 times 7 is 0, 1 times 7 is 7, 2 times 7 is 14, 3 times 7 is 21, but 4 times 7 is 28, and 28 modulo 27 is congruent to 1. So the inverse of 7 in modulo 27 is exactly 4, and therefore dividing by 7 is the same as multiplying by 4. This is another good example of how we can simplify our life by thinking about large numbers. 20 times 4 is the same as minus 7 times 4. This is minus 28. Then we add 27 once to get minus 1, and minus 1 modulo 27 is simply plus 26. There is, however, a smarter way to find inverses, if you want to be a little bit more mathematical, and that is called the Euclidean algorithm. I will demonstrate it on an example. Let's suppose that we want to find the inverse of 20 modulo 27. To do this, I take these two numbers, 27 and 20, in descending order. So I take the larger number first, and then I want to divide this larger number with remainder by the smaller number. And 20 goes only one time into 27, and we get a remainder of 7. So we have this division with remainder. Now we take the last two numbers, 20 and 7, and we repeat the exact same process for them. This would give us 2 times 7 plus a remainder of 6. Again, we take 7 and 6, the last two numbers, and again we divide with remainder. Now we get 1 times 6 plus 1. We take 6 and 1, the last two numbers on the previous line, we divide with remainder, and this time we get remainder 0. Once we get remainder 0, the algorithm ends. Now, having all of these equations, we can use them to reconstruct the inverse of 20. We start by taking the last equation before we reach 0, so the one which has 7 on the left hand side, and expressing 1 using the other two numbers. In this case, we get that 1 is equal to 7 minus 6. Then we go to the equation above that. And now, from this one, we can express 6 as 20 minus 2 times 7. Combining this with the previous equation allows us to write that 1 is equal to minus 20 plus 3 times 7. And now, from the very first equation, we can express 7 in terms of 27 and 20. And simplifying this gives us an expression of this form, which expresses 1 in terms of 27 and 20, the two numbers that we started with. And this is now going to reveal what the inverse is. Why? Well, because we're looking for the inverse modulo 27. And if you look at this part is divisible by 27. So this is a multiple of 27, which means that modulo 27, this entire green thing, is equal to 0, and just disappears. So modulo 27, 1 is equal to minus 4 times 20. And this means that the inverse of 20 is minus 4, or in other words, plus 23. So to finish up, let's take a look at something slightly more advanced, which may, however, be helpful, namely Fermat's little theorem. This is the same Fermat who is quite famous for his so-called last theorem, which turned out to be somewhat tricky to prove. But in contrast to that, the little theorem is quite straightforward to show, and it is part of any first-year algebra course. And what it says is basically this. If we have any two integers, a and p must be a prime, but a can be pretty much anything, then a to the power p is congruent to a modulo p. For example, since 17 is a prime, then 15 to the power 17 is the same as 15 modulo 17. This may be slightly tricky to use in practice because you need to be exponentiating to the same p that you're modulating with. But on the other hand, if you have something like 15 to the power 20 modulo 17, you can express this as 15 to the power 17 times 15 to the power 3. And then the 15 to the power 17 basically goes away. So occasionally you can use this to simplify your calculations as well. So that's pretty much it. Of course, there are many more advanced theorems and techniques that can be used to tackle more complicated problems, but what you've seen so far should be quite enough for tackling practical problems on an exam. And in particular, it should be sufficient to pass my exam, which you may be about to take if you're watching this video. And if you are, then good luck. In any case, hope you enjoyed the video and see you next time.